look at the flame of a candle. Or if you're outside, look up at the moon hanging in the dark sky. It feels immediate, doesn't it? You turn your head, the light hits your retina, and your brain says, there is the moon. It feels like a direct, instantaneous connection, as if your consciousness is reaching out and touching the object of your attention. But it is not. That feeling of immediacy is an illusion, a very convincing trick played by the scale of our daily lives. In reality, you're not seeing the moon as it is now. You're seeing a ghost. You're seeing a version of the moon that existed 1.3 seconds ago. If you look at the sun, you're seeing a ghost from 8 minutes ago. If you look at the stars, you're looking into a deep, ancient history. We often talk about the speed of light as a technicality, a number in a textbook that engineers use to calculate delay in fiber optic cables. 299,792,458 meters per second. It is a very precise number. It is not an approximation. We've defined our meter based on it. But to think of it merely as a speed is to miss the profound beauty of what this limit actually represents. It is not just the speed limit of a photon, it is the speed limit of reality itself. It is the update rate of the universe. Think of it this way. Imagine the universe is a calm, dark lake. You are a boat floating in the middle of this lake. If something disturbs the water on the far shore, a rock falling in, a fish jumping, the water right next to your boat does not move instantly. The information that an event has occurred must travel across the surface in the form of a ripple. That ripple is the messenger. Until that ripple reaches you, as far as you are concerned, the rock has not fallen. The event has not happened in your slice of reality. Light is exactly like that ripple. It is the mechanism by which the universe informs one part of itself that something has happened in another part. This brings us to a rather unsettling realization. We are largely disconnected from the present moment of the cosmos. We live in a bubble of now that is incredibly small. The further out we look, the further back we drift. This is often framed as a limitation, a prison wall that keeps us from exploring the galaxy, and indeed, as we've discussed before, it is the primary reason why human civilization will likely never leave the local area of our solar system. We are trapped by the vastness of the space and the finiteness of the speed. But there's a flip side to this. This limit, this delay, is the only reason anything makes sense at all. Now, ask yourself, if the sun disappeared this exact second, simply vanished from existence, how long would you keep feeling its warmth? It is a terrifying thought, isn't it? The massive star that holds our solar system together, the source of all our energy gone in a blink. Logic might tell you that if the source of gravity is gone, the Earth should instantly fly off into the dark void. But that is not what would happen. For 8 minutes and 20 seconds, the Earth would continue to orbit a ghost. The gravitational pull would still be felt. The light would still shine in our sky. The plants would still photosynthesize. People on the beach would still get sunburned. For 8 minutes, we would be living in a reality that no longer exists, worshipping a dead god, orbiting a vacuum. It is only when the last ripple of gravity and the last photon of light, traveling together at the cosmic speed limit, finally cross the 150 million kilometers to reach us, that the sky would suddenly go black and the Earth would be flung from its orbit. This lag tells us something fundamental about the structure of the universe. It tells us that space is not just emptiness. It is a medium. It has properties. In the 19th century, a Scottish physicist named James Clerk Maxwell sat down with a pen and paper and did something that I consider to be one of the greatest intellectual feats in human history. He wasn't looking for the speed of light. He was looking at electricity and magnetism. He realized that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They leapfrog over each other. He calculated the speed at which this leapfrogging wave would travel through the vacuum. He found that the speed depended on two numbers, the permittivity of free space and the permeability of free space. These are essentially measurements of how much the vacuum resists the formation of electric and magnetic fields. It is like the thickness of the water in our lake analogy. When Maxwell crunched the numbers, out popped a speed, roughly 300,000 kilometers per second. Maxwell looked at this number and realized it was suspiciously close to the measured speed of light. In a moment of quiet revelation, he realized that light itself was just a ripple in the electromagnetic field. But here is where the story shifts from classical physics to the mind-melting reality that Richard Feynman would later explore. Why is the speed that specific number? Why not infinite? Why not instantaneous? If the speed of light were infinite, the concept of cause and effect would collapse. If information could travel instantly, everything would happen at once. There would be no separation between the match being struck and the forest burning. There would be no history. There would be no unfolding of a story. The speed of light acts as a cosmic chaperone, ensuring that events occur in an order, that there is a before and an after. It prevents the universe from being a chaotic singularity of happening. It stretches events out across the fabric of space-time so that they can be experienced. So, when we look at that limit, we shouldn't see it as a barrier preventing us from having Star Wars galactic empires. We should see it as the structural integrity of our existence. It is the walls of the house that allow us to live inside. Without it, the roof falls in. However, calling it a speed limit is actually a bit misleading. It suggests that you can go faster, but the police or the laws of physics will stop you. It suggests there is a force holding you back. But that isn't the case. As we begin to peel back the layers of reality, we see that c, this constant, is not really about speed. It is about geometry. It is about the relationship between space and time. Imagine you're in a car driving across a flat, endless salt flat. You can drive north or you can drive east. If you drive strictly north at 100 kilometers per hour, you're making maximum progress to the north. If you turn and drive northeast, you're splitting your speed. You're making some progress north and some progress east. But your total speed is still 100. Now imagine that north is movement through time and east is movement through space. Everything in the universe, including you, including the device you're listening to this on, is moving through the combined fabric of space-time at exactly the speed of light. Right now, you're sitting still in your chair. You're not moving through space. Therefore, all of your motion is being used to move through time. You're aging at the maximum possible rate. You're traveling towards tomorrow at the speed of light. But if you stand up and start walking, you're diverting a tiny, tiny fraction of that speed into motion through space. Because you're now moving through space, you must, by the laws of geometry, move slightly slower through time. Probably don't feel it because walking speed is negligible compared to the speed of light. But if you could get in a spaceship and travel at 99% of the speed of light through space, you would have almost no speed left to move through time. You would be frozen in the now while the rest of the universe aged millions of years around you. This is the first hint of the strange world Feynman inhabited. We tend to think of objects as solid things moving through a void, but in this view we're all just trajectories. We are lines drawn on a four-dimensional piece of paper. The speed of light is the rule that says the line must always be a certain length. You cannot change the length of the arrow, you can only change the direction it points. And this brings us back to the photon, the particle of light. If you're a photon, you have no mass. You have no weight to hold you back. You're compelled by the very nature of your existence to use all of your motion through space. You pour 100% of your capacity into the east direction of our analogy. This means you have zero motion left for the north direction. You have zero motion through time. Think about that for a moment. Really let it sink in. From the perspective of a photon, time does not exist. A photon created in the core of a star 1 billion years ago, which then travels across the dark void of the cosmos to hit your eye tonight, experiences no duration. For the photon, the moment of its birth and the moment of its death on your retina are the same moment. It is instantaneous. The universe, to a beam of light, is 0 pixels wide and 0 seconds long. It is we, the slow, heavy, massive creatures who are trapped in time. We are the ones who have to wait. We are the ones who experience the separation. This separation is what gives us our humanity. It is what gives us the ability to yearn, to wait, to remember. If we were like light, there would be no memory, because there would be no past. There would just be an eternal, singular flash of existence. So, in a very real sense, our inability to reach the speed of light is what grants us the gift of a life. It grants us the duration in which to fall in love, to learn, to make mistakes, and to look up at the stars and wonder. But even this beautiful picture of relativity, of space and time trading places, is not the whole story. It was the story for the early 20th century, the story Einstein gave us. But then came Richard Feynman, A man who didn't just look at the geometry of the universe, but looked at the machinery under the floorboards. He asked a simpler, perhaps more innocent question. How does the light know where to go? When we turn on a laser pointer and aim it at the wall, we see a straight line. We learn in school that light travels in straight lines. It takes the shortest path between A and B. This is called Fermat's principle of least time. It seems obvious. The light wants to get there, so it takes the quickest route. But how does the light know which route is the quickest? Imagine you are a lifeguard on a beach. A swimmer is drowning in the water. You're on the sand. You can run faster on the sand than you can swim in the water. To save the swimmer in the least amount of time, you shouldn't run in a straight line directly at them, because that would maximize your time in the slow water. You should run a bit further down the beach, staying on the fast sand longer, and then dive in at an angle that minimizes the swim. Lifeguards do this intuitively. Light does this mathematically. When light goes from air into water, it bends, it changes direction. We call it refraction. It is finding the path of least time. But this implies something almost magical. It implies that the photon, before it starts its journey, somehow calculates all possible paths, measures the resistance of the air, the glass, the water, and then chooses the optimal one. But a photon has no brain. It has no calculator. It is a fundamental packet of energy. How can it know the future geometry of the space it hasn't entered yet? This is where the campfire story takes a turn into the strange. This is where the intuition we have built up, of ripples on a lake, of cars on a salt flat, starts to melt away, revealing something far more fluid and far more bizarre underneath. Feynman didn't look at light as a particle that makes a decision. He looked at it as an explorer that tries everything. Here is a number that might scare you. Infinite. Not just a very big number, but truly infinite. Feynman proposed a radical idea called the sum over histories. He suggested that when a particle of light goes from a lamp to your eye, it doesn't just take the straight line path. It takes every path. It takes the path where it goes straight to your eye. It takes the path where it bounces off the ceiling first. It takes the path where it circles the room 3 times. It takes the path where it travels out the window, goes to the moon, bounces back, and hits your eye. It takes the path where it goes to the edge of the universe and back. It sounds absurd. It sounds like madness. If light took all those paths, surely we would see a chaotic mess of brightness everywhere. We wouldn't see a sharp image of the lamp. We would see a blur of the entire universe. But Feynman showed that the universe is a master of cancellation. Imagine a choir of 1 million people. If they all sing slightly different notes at slightly different times, the sound becomes a noise, a rumble that cancels itself out. Silence. But if a group of them sing in perfect harmony, that sound rises above the noise and is heard. In Feynman's view, the crazy paths that light takes, the detours to Mars, the loops around the room, are like the singers who are out of tune. Their phases cancel each other out. The path to Mars takes a certain amount of time. A path slightly to the left of Mars takes a slightly different amount of time. These differences cause the waves of probability to interfere destructively. They kill each other. They sum to 0. The universe essentially vetoes these paths. But near the path of least time, that straight line we see, the paths are all very similar. A path that is 1 millimeter to the left of the straight line takes almost exactly the same time as the straight line. Because the times are so similar, the waves reinforce each other. They harmonize. They amplify. So the straight line of light is not a rule. It is not a law that the photon must obey. It is simply the only path that survives the chaos. It is the path of constructive interference. Reality, the solid, predictable world we see around us, is just the thin slice of probability where the math didn't cancel out. This changes our perception of the limit entirely. We aren't just looking at a speed limit imposed by a traffic cop. We are looking at a fragile consensus. The beam of light is a democracy of infinite possibilities, all voting on where to go, and the result is the straight line. But what happens when you mess with the democracy? What happens if you block some of those paths? This is where Feynman's mind truly melts ours. If you take a barrier and cut 2 tiny slits in it, you're forcing the light to choose. You're limiting the infinite paths down to 2 main options. And when you do that, the light stops acting like a particle and starts acting like a wave of probability, creating interference patterns on the wall. This tells us that the universe is not made of solid things, it is made of possibilities. The speed of light is the thread that stitches these possibilities together into a coherent picture. It is the loom on which the fabric of reality is woven, And this weaving process is continuous. It is happening right now, in the space between your ear and the speaker, in the space between your eyes and the screen. The universe is constantly exploring every possible option, rejecting the ones that don't fit and presenting you with the most likely outcome. You are living in the path of least resistance. But let's go back to that feeling of melancholy we started with. The idea that we are trapped. The idea that we are seeing ghosts. Feynman's perspective adds a new layer to this. We are not just seeing ghosts of the past, we're seeing the survivors of a journey. Every photon that hits your eye has survived a journey through the infinite. It has navigated the sum of all histories to deliver a tiny packet of energy to your retina. It is a miracle that we see anything at all. It is a miracle that the universe is transparent to us. If the cancellation didn't work, if the interference wasn't perfect, we would be blind, lost in a white noise of light. So, the speed of light is the limit, yes. But it is also the protector. It protects causality. It protects history. And as we will see, it protects the very structure of matter itself. Because if light didn't have this limit, if E didn't equal mc squared, atoms wouldn't hold together. The stars wouldn't shine. Life would be impossible. We often resent the walls of our prison. We look at the stars and wish we could go there instantly. We wish we could warp speed across the galaxy. But we forget that the walls are what hold the roof up. The restrictions of the universe are the instructions for how to build a human being. In the next part of our journey, we're going to look closer at what happens when you try to fight these walls. We're going to conduct a thought experiment. We're going to build a machine, a theoretical engine, and we are going to try to push a human being up against that barrier. We are going to see what happens to your watch, your heart, and your perception of the universe when you dare to approach the speed of light. We will see that the closer you get to the edge, the more the universe contorts itself to stop you. Not out of malice, but out of necessity. Because to break the speed of light would be to break the logic of existence itself. The sun is still shining in our sky, the ghost is still warm, the ripple is still moving across the lake, and we are here, in our boat, watching the waves come in, trying to understand the ocean. So, let's imagine we decide to sail across it. Let's imagine we are tired of simply looking at the ghost of the past, and we want to catch up to the present. We are going to build a machine, a spaceship, and not just any spaceship, but the ultimate machine, unbound by the limitations of current technology. We have infinite fuel. We have an engine that never overheats. We have a hull that is indestructible. We strap ourselves into the pilot's seat to look out into the stardusted void, and we slam the throttle forward. We want to break the speed limit. We want to see what lies on the other side of light. At first, everything feels normal. You're pushed back into your seat. The stars streak by, the speedometer climbs, 10% of the speed of light, 50%, 90%. You're moving at 270,000 kilometers per second. You feel powerful. You're outrunning time itself. But then, something strange begins to happen. You don't feel it inside the ship. To you, your watch is ticking normally, your heart is beating at the same rhythm, but back on Earth, the mission control team is watching your telemetry with growing confusion. They see you pouring more and more energy into the engines. They see the fuel gauge dropping rapidly. They see the thrust output screaming at maximum. By all the laws of motion we learn in high school, you should be accelerating, but you aren't. Or rather, you're accelerating but barely. It is as if the ship has suddenly driven into a pool of molasses. You push harder, but the speed hardly budges. You reach 99%, then 99.9, then 99.999. You're pouring the energy of entire stars into your engines, but the needle on the speedometer refuses to touch the line. What is happening? Is the engine broken? Is there a drag from the vacuum of space? No. What is happening is that the universe is changing the rules of the game to stop you. Einstein gave us an equation that everyone knows, but very few people truly feel in their bones. E equals mc squared. Energy equals mass times the speed of light squared. We usually think this means that mass can be turned into energy, which is how nuclear bombs work. But the equal sign goes both ways. Energy is mass. They are the same thing, just in different clothes. As you pump energy into your ship to make it go faster, you're adding kinetic energy to the system. But because nature forbids you from going faster than light, that energy has to go somewhere else. It doesn't disappear. Instead, it condenses. It solidifies. It turns into mass. Here is a perspective shift that might unsettle you. The faster you move, the heavier you get. If you were running down the street and approaching the speed of light, you wouldn't just be fast, you would become incredibly dense. In our spaceship, as we hit 99% light speed, the energy we are feeding the engines is no longer making us go much faster. It is making the ship more massive. We are pushing a boulder that is growing into a mountain. If we try to reach 100%, our mass would become infinite. And to move an infinite mass, you need infinite energy. Since there is not infinite energy in the universe, the feat is impossible. The universe prevents you from breaking the law by simply making you too heavy to move. But why? Why does the universe care so much? Why go to all this trouble, increasing mass, warping time, shrinking space, just to keep us below this specific speed? To understand this, we have to stop thinking of speed as distance divided by time. We have to start thinking like a cartographer. Imagine you're standing on a vast flat sheet of graph paper. This paper represents space-time. Now, imagine there is a permanent rule. You must always be moving at a constant speed across this paper. You cannot stop. You cannot slow down. You cannot speed up. You are locked at one specific velocity, the speed of light. This sounds wrong, doesn't it? You're sitting in a chair right now. You aren't moving at the speed of light. You aren't moving at all. But remember, the paper is space-time. It has 4 directions. 3 of them are spatial, northeast, up. But the 4th direction is time. When you are sitting still in your chair, you are not moving through space. All of your constant velocity is pointed directly along the time axis. You're flying through time at the speed of light. That is why you age. That is why tomorrow comes. You're hurtling toward the future at maximum velocity. Now suppose you stand up and start walking north. You're changing your direction on the graph paper. You're now moving a little bit through space. But because your total speed across the paper must remain constant, you have to borrow that speed from somewhere. You have to borrow it from your motion through time. It is like walking on a compass heading. If you're walking due north, you're making maximum progress north. If you turn slightly east, you're now splitting your speed. You're making some progress east, but you must, by definition, be making less progress north. This is the secret of relativity. Motion through space comes at the cost of motion through time. The faster you move through space, the slower you move through time. Again, at walking speeds, this trade-off is tiny. But in our spaceship, at 99% of the speed of light, we have diverted almost all of our resources into the space direction. We have almost nothing left for the time direction. This is why, if you return to Earth after what felt like a 1-year journey at that speed, you would find that centuries had passed for everyone else. You weren't travelling into the future, you just stopped experiencing the passage of time while everyone else continued. You took a shortcut through the 4th dimension. But this analogy reveals something even more profound about the limit. People often ask, what if we build a better engine? What if we find a loophole? Asking, why can't I go faster than light, is exactly like standing at the North Pole and asking, why can't I go further north? It isn't a question of technology. You can have the best boots in the world. You can have a jetpack. It doesn't matter. Once you're at the North Pole, every direction you step is south. North ceases to exist as a direction you can travel. In the same way, once you're moving at the speed of light through space, you've rotated your velocity vector completely. You're moving 100% through space and 0% through time. There is no more speed to be had. There is no faster. The geometry of the universe simply runs out of road. This realization is both beautiful and claustrophobic. It confirms that we are living in a geometric structure, a shape. We are not free actors on an open stage. We are pieces moving along the lines of a specifically curved board. Now, ask yourself, what does the universe look like to someone pushing up against that edge? If you were inside that spaceship, looking out the front window, the view would be terrifying. Because you're catching up to the light in front of you, the light waves get squashed. They turn blue, then violet, then ultraviolet. Eventually, the gentle starlight in front of you would shift into hard X-rays and deadly gamma radiation. The visible universe ahead of you would fade into a dark, invisible radioactive death beam. Behind you, the light would be stretched out. The stars would turn red, then infrared, then fade into radio waves. The universe would go dark behind you. You would be flying through a tunnel of nothingness, squeezed between a past you can no longer see and a future that is trying to kill you with radiation. This is the universe telling you, you do not belong here. This barrier, this sea, is the event horizon of our causal reality. It keeps things separate. It ensures that the influence of an event, a star exploding, a person waving hello, cannot outrun the event itself. If we could travel faster than light, we could outrun the signal of our own birth. We could turn around and watch ourselves being born. We could, in theory, send a message back to prevent it. We would break the chain of cause and effect that allows the universe to make sense. So, the speed of light is not just a number. It is the guardian of logic. It is the wall that keeps the paradoxes out. But Richard Feynman, with his mischievous grin and his bongo drums, wasn't satisfied with just looking at the big, heavy walls of relativity. He wanted to know what the bricks were made of. He wanted to know what was happening at the smallest possible scale, down where the photons themselves were playing their games. While Einstein showed us the geometry of the macro, the big picture of space and time, Feynman took us into the micro, the quantum realm. And if you think time slowing down and mass becoming infinite is strange, what Feynman found will make that look like common sense. You see, Einstein's universe is smooth. It is predictable. It is a curved sheet of paper. But Feynman's universe, the universe of quantum electrodynamics, is a chaotic, buzzing, impossible mess. In Einstein's world, if you throw a ball, it follows a curve. In Feynman's world, if you throw a photon, it doesn't just follow a curve. It follows every curve. Remember our boat on the lake. In the classical view, the boat travels from the dock to the island in a straight line. But Feynman realized that at the quantum level, the boat effectively teleports to the moon, swims in the ocean, visits the sun, and dances on the surface of Mars, all before arriving at the island. And the only reason we see it go in a straight line is because all those other crazy adventures cancel each other out. This concept, the path integral, changes our understanding of the limit entirely. It suggests that the speed of light isn't just a rule imposed from the top down. It is a result emerging from the bottom up. It is the average of an infinite number of chaotic choices. We often think of the laws of physics as rigid bars on a cage, but Feynman showed us that they are more like the rules of an improvisational jazz band. The individual notes, the particles, are doing wild, unpredictable things. But when you step back and listen to the whole band, a rhythm emerges. That rhythm is the speed of light. That rhythm is reality as we know it. But this raises a haunting question. If reality is just the sum of infinite possibilities, how stable is it really? Are we standing on solid ground, or are we standing on a thin sheet of ice over a deep, dark ocean of chaos? What Feynman uncovered suggests that the solid world we live in is actually a very delicate balance. The light beam that lets you see the face of someone you love is only stable because trillions of probability waves are agreeing to cooperate. If that cooperation were to slip, even for a nanosecond, the image would dissolve, the face would disappear, the connection would be broken. We are accustomed to thinking of the universe as a machine that was built and then left to run, but the quantum view suggests something more active. It suggests that the universe is being constantly performed. It is being knitted together, moment by moment, by the frantic interaction of these particles. The speed of light is the tempo of that performance. And just like in music, the silence is as important as the sound. The limits are as important as the freedom. As we prepare to dive deeper into Feynman's mind in the next part of our journey, I want you to hold on to this image. You're not just an object moving through a static void. You're a collection of infinite possibilities, collapsing into a single reality, travelling through time at the speed of light, held together by the fragile geometry of a universe that is desperately trying to keep its story straight. We have looked at the walls of the prison. Now we are going to look at the inmate. We are going to look at the photon itself and the impossible dance it performs every time you blink your eyes. Because it turns out the universe doesn't just have a speed limit, it has a sense of humour, and the joke is on us. The year was 1965. Richard Feynman, a man who played bongos at parties and picked locks for fun, stood up to accept the Nobel Prize in Physics. He had done something that on the surface seemed impossible. He had taken the rigid, geometric universe of Einstein, that smooth, predictable sheet of paper we talked about, and he had shown us what was underneath it. And what he found was not smooth. It was a riot. If Einstein is the architect who designed the beautiful curved walls of our reality, Feynman is the guy who crawled into the crawl space and found out that the walls are actually made of vibrating, chaotic energy. Now ask yourself, have you ever wondered why a mirror works? It seems like a silly question. You look in the bathroom mirror and you see your face. Light hits your cheek, travels to the glass, bounces off and comes back to your eye. Simple reflection. Angle of incidence equals angle of reflection. We learn this in school with diagrams of straight lines and little arrows. It feels safe. It feels logical. But Richard Feynman looked at that mirror and asked, how does the photon know where the middle is? Think about it. A mirror is just a shiny surface. It is made of atoms. Why does the light bounce off at that specific angle? Why doesn't it bounce off at a random angle? Why doesn't it scatter like a tennis ball hitting a rocky road? To answer this, Feynman developed a theory called quantum electrodynamics, or QED. He called it the strange theory of light and matter, and honestly, strange is an understatement. Feynman suggested that when a photon leaves your face and heads toward the mirror, it doesn't just hit the middle of the glass. It hits the left side. It hits the right side. It hits the very edge of the frame. In fact, it hits every single point on that mirror simultaneously. This is the sum over histories. The photon doesn't have a path. It has all paths. Imagine you are trying to walk from your house to the grocery store. In our normal life, you take the sidewalk. You walk in a straight line because it is the shortest distance. But in Feynman's quantum world, if you were a photon, you would also walk to the store via the moon. You would walk to the store via the center of the Earth. You would walk to the store by first circling the Andromeda Galaxy. You would take every possible route that geometry allows all at the same time. It sounds like insanity. If light did that, the universe would be a blur. We wouldn't see anything. But here is the magic trick. Each of these paths has a clock associated with it. Imagine a little stopwatch attached to the photon. As the photon travels, the hand on the stopwatch spins. Round and round it goes. When the photon arrives at your eye, the hand stops pointing in a certain direction, say 3 o'clock. Now, let's look at the crazy paths. The path to the left edge of the mirror is much longer than the path to the middle, so the stopwatch spins more times. Maybe it lands at 6 o'clock. The path just next to it is slightly different, so the stopwatch lands at 12 o'clock. When Feynman added all these arrows together, the 6 o'clock arrow and the 12 o'clock arrow, they pointed in opposite directions. They cancelled each other out. It's like pushing a swing. If you push when the swing is coming back, you stop it. The crazy paths are out of sync. They destroy each other. They vanish into the quantum noise. But, and this is the melt your mind moment, look at the middle of the mirror. The path exactly in the center is the shortest, but the path just 1 millimeter to the right of the center is almost the same length. It's barely different. So the stopwatch on that path points to 3 o'clock, and the stopwatch on the neighbor path points to 3:01. They are pointing in almost the same direction. They don't cancel. They add up. They reinforce. The reason you see your reflection in the mirror is not because light travels in a straight line. It is because the center of the mirror is the only place in the universe where the infinite histories of the photon agree with each other. The reality you see, the stable, consistent world, is just the tiny slice of the universe where the chaos happens to harmonize. But what if I told you that the light hitting your eye right now took a detour to Mars before it got to you? Technically, according to the math of QED, there is a non-zero contribution to the light you see from a path that went to Mars and back. It is incredibly small. It is vanishingly tiny. But it is there. The math demands it. The light that illuminates your room right now is, in a very real mathematical sense, sniffing out the entire universe to find the path of least time. This changes everything about how we view the limit of light speed. We tend to think of the speed of light c as a barrier that stops us, a wall. But in Feynman's view, c is the conductor of the orchestra. It is the rule that determines how fast those little stopwatches spin. If the speed of light were different, the stopwatches would spin at a different rate. The cancellation wouldn't work the same way. The straight lines would dissolve. If the speed of light were infinite, the stopwatches wouldn't spin at all. Every path would take 0 time. Every arrow would point in the same direction. The cancellation would fail completely. You would be bombarded by light from every point in the universe simultaneously. The night sky would be blinding white. The structure of matter would fall apart because the electromagnetic forces holding your atoms together rely on this same exchange of photons. So, the limit is not a cage. It is a filter. It filters out the infinite chaos of the quantum world and leaves us with this beautiful, coherent, slow-moving story called life. But Feynman didn't stop at mirrors. He applied this to everything. He looked at 2 electrons repelling each other. You know the feeling, try to push 2 magnets together, with the same poles facing. You feel that invisible cushion, that springiness. In classical physics we say there is a field there, a force field. But Feynman said no, there is no field. There are just particles throwing things at each other. Imagine two ice skaters standing on a frozen lake. One skater throws a heavy bowling ball to the other. When she throws it, she recoils backward. When the other skater catches it, he's knocked backward. To a watcher far away who can't see the ball, it looks like a mysterious repulsive force was pushing them apart. Feynman said that is what electricity is. Electrons are throwing photons at each other. They're trading particles of light. And since light travels at a finite speed, that exchange takes time. It isn't instant. This is where the speed limit becomes the speed of reality. If the skaters could throw the ball infinitely fast, the interaction would be instantaneous. But they can't. The ball has to travel. The force has to propagate. This brings us to a terrifying realization about the stars. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. We know this. But under Feynman's rules, the connection is even more fragile. The gravitational pull that Andromeda exerts on the Milky Way, the pull that will eventually cause them to crash into each other, is mediated by gravitons, theoretical particles that act like our bowling ball. These particles are streaming across the void at the speed of light. They are the stitches binding the two galaxies together. If the speed of light were to suddenly change, or if it were infinite, the gravitational structure of the universe would shatter. The galaxies wouldn't know how to orbit each other. The news of where the masses would arrive too early or too late. The dance would turn into a pile-up. But the most mind-bending part of Feynman's legacy is what this says about empty space. We think of the vacuum of space as empty, a void, nothingness. But if you take Feynman's sum over histories seriously, you realize that nothing is actually everything. Even in the darkest, emptiest box in the universe, where there are no atoms and no light, the fields are still there. And because of the uncertainty principle, these fields are constantly bubbling. Virtual particles, ghost photons, ghost electrons, are popping into existence, travelling for a tiny fraction of a second and then vanishing again. They're borrowing energy from the vacuum and paying it back before the universe notices. Empty space is heavier than you think. It is seething with activity, and this activity is governed by c. The speed of light determines how far these ghost particles can travel before they have to disappear. It defines the reach of the vacuum. So, when we sit here on Earth and lament that we cannot travel faster than light, that we cannot visit the stars, we are missing the point. We are like fish complaining about the water. The water is what supports us. The limit is what allows us to exist. If we could break the speed limit, we wouldn't just be faster. We would unmake the vacuum. We would unravel the tapestry of virtual particles that gives the universe its baseline energy. We would potentially trigger a collapse of the vacuum itself, a bubble of true nothingness that would expand at the speed of light and delete the universe. So perhaps it is a good thing we're stuck. Perhaps the walls of the prison are actually the hull of the submarine, keeping the crushing pressure of the infinite out. But there is one more layer to Feynman's insight that connects directly to our human experience. It's about probability. In the classical world, if you know the position and speed of every particle, you can predict the future perfectly. The universe is a clockwork machine. If you know the state of the universe now, you know the state of the universe forever. Feynman destroyed that. By showing that light takes every path, he introduced a fundamental fuzziness to reality. You cannot predict exactly where the photon will land. You can only predict the probability. You can say, there is a 95% chance it will hit the middle of the mirror, but there is always that tiny, tiny chance it will hit the edge. This means the future is not written. It is not a script we're just reciting. It is a game of chance. It is open. And this brings us back to the beautiful prison we will explore in the final part. The speed of light limits our movement through space, yes. It traps us in our solar system. But by limiting the transfer of information, by forcing the universe to choose a path, it creates the possibility of the unexpected. It creates the now. Without the limit, the past, present, and future would all be accessible. Everything would be a static block of happening. But because light takes time to travel, because information is delayed, we have this precious, fleeting sensation of the present moment. We have the unknown. And isn't that what makes life worth living? The fact that we don't know what's coming next. The photon doesn't know which path it will effectively take until it hits your eye. The universe decides in the moment of observation. In a way, by looking at the world, you're forcing the universe to make up its mind. You're collapsing the infinite possibilities into a single reality. You're not just a passive observer in a boat on a lake. You are the one deciding where the waves break. In the final part of our journey, we are going to pull all these threads together. We are going to look at why this limit, this specific number, this specific geometry makes us who we are. We are going to stop looking at the stars with envy and start looking at them with recognition. We are going to see that being trapped on Earth in this slow, heavy, beautiful timeline is not a punishment. It is the only way a story like ours could ever be told. We will see that while we cannot cross the galaxy, we can hold the entire concept of the galaxy inside our minds. And maybe, just maybe, that is enough. So let's sit with that thought for a moment. We often talk about the speed of light as if it were a technical glitch, a software bug in the universe that prevents us from having the infinite freedom we crave. We look at the stars and we feel a pang of sadness because we know that even the fastest ship imaginable would take lifetimes to cross the void. We feel small, we feel slow, we feel locked in. But what if we are looking at this upside down? What if the speed of light isn't a cage but a cradle? Imagine for a second that we got what we wanted. Imagine that tomorrow the speed of light became infinite. The c in our equations changes to infinity. Suddenly, there is no delay. Information travels instantly from one end of the cosmos to the other. At first glance, this sounds like paradise. We could talk to aliens in the Andromeda Galaxy in real time. We could teleport to the edge of the visible universe. But think about what that actually means for the structure of reality. If the speed of light is infinite, then time, as a dimension that separates events, effectively collapses. The separation between cause and effect vanishes. The match is struck and the forest is ash and the wood is growing, all in the same zero-duration instant. Without the speed limit to stretch events out, the universe becomes a singularity of happening. Everything happens at once. There is no unfolding and there is no story. It would be like taking a beautiful 1,000-page novel and printing every single word on the same page, one on top of the other. It wouldn't be a story anymore. It would just be a black blot of ink. The speed of light is the page number. It is the spine of the book. It is the mechanism that ensures page 1 comes before page 2 and that the end doesn't happen at the beginning. It creates the necessary friction that allows time to exist. So, in a very literal sense, the speed limit is the only reason you have a past to remember and a future to hope for. We are not trapped by the limit, we are defined by it. But the protection goes deeper than just time. It goes down to the very atoms in your body. Remember Einstein's equation E equals mc squared. Energy is mass times the speed of light squared. That little c is a multiplier. It is a scaling factor. It tells us how much energy is locked up inside a tiny bit of mass. Because c is a huge number, a tiny amount of mass holds a huge amount of energy. This is why the sun shines. It converts a tiny bit of mass into a lot of light. Now ask yourself, what would happen to you if that number changed? If the speed of light were lower, say the speed of a car, then E equals mc squared would yield a very small number. The energy binding your atoms together would be weak. The electrical forces that hold your molecules in place would be sluggish. You wouldn't be able to stand up. Your body would simply dissolve into a mist of loosely associated particles. The structural integrity of matter depends on the high velocity of the force-carrying particles. You exist as a solid being only because the speed of light is high enough to glue you together. So, this prison we complain about is actually a suit of armour. It is the pressure vessel that keeps us from evaporating into the void. This brings us back to Richard Feynman and his sum over histories. We learned that reality is a consensus, a probability game where the universe explores every path and settles on the most likely one. But there's a beautiful philosophical implication here that Feynman often hinted at. If the future were perfectly determined, if we were just cogs in a machine, the universe would be boring. It would be a movie playing on a screen with no one watching. But because of the uncertainty, because of the fuzziness, the future is not yet written. The photon has not decided where to land until it lands. This suggests that the universe is not a finished product. It is a work in progress, and we are on the cutting edge of that progress. We, the slow, massive, lumbering creatures who cannot move at light speed, are the observers. We are the ones who force the universe to decide. When you look at a star, you are the final destination of a journey that lasted 1 billion years. You are the reason the wave function collapses. You are the anchor. There is a concept in physics called the block universe, where the past, present and future all exist simultaneously, like a block of ice. In this view, our experience of moving through time is just a trick of consciousness, like a spotlight moving across a dark stage. The actors are all there, frozen in the dark, waiting for the light to hit them. If this is true, then the speed of light is the speed of that spotlight. It is the refresh rate of our consciousness. It is the tempo of the music. And you cannot enjoy a symphony if you play it all in 1 second. You need the duration. You need the pauses. You need the adagio. We are the entities that get to experience the adagio. The photon, zooming across the universe, experiences everything in an instant. It has no time for reflection. It has no time for love. It has no time for grief. It just is. But we, trapped in the slow lane, we get to feel the passage. We get to watch the sunset change colour. We get to watch our children grow. We get to learn. We get the privilege of the process. So when we build our telescopes and look out at the impossible distances, we shouldn't feel defeated. We shouldn't feel like prisoners looking through the bars. We should feel like the audience in the best seat in the house. The vastness, the separation, the silence between the stars, that is the acoustic design of the theatre. It is built that way so that the music sounds right. And what about the melting your mind promise? What is the final takeaway from Feynman's strange world? It is this. The world you see around you, the chair, the wall, the hand in front of your face, looks solid. It looks static. But it is actually a roaring ocean of activity. It is a frantic exchange of energy, a chaotic dance of infinite possibilities, all happening at a speed we cannot comprehend, all balancing on the razor's edge of probability. The only thing that keeps it stable, the only thing that keeps the you of 5 seconds ago connected to the you of right now is this cosmic constant. We are surfing on the crest of a wave called C. If we could break the limit, if we could go faster, we wouldn't find freedom. We would find noise. We would break the surface of the wave and drown in the chaos of the quantum foam. We would lose the very thing that makes us human, our continuity. So let us make peace with the wall. Let us stop banging our fists against the speed of light. Instead, let us lean against it. It is strong. It will hold us. The universe has given us a very specific playground. It has boundaries, yes, but those boundaries are what make the game playable. We have a finite amount of time, and we have a finite speed, and because of that our choices matter. If we could go everywhere instantly, being here would mean nothing. But because it takes effort to get to the other side of the world, because it takes time to send a message to Mars, the act of doing so has value. The distance gives weight to our actions. The light from the stars is not taunting us. It is waiting for us. It has travelled across the sum of all histories, dodging cancellation, navigating the void, just to interact with your eye, just to be part of your story. We are not cosmic mistakes trapped on a lonely rock. We are the universe's way of slowing itself down. We are the mechanism by which the cosmos pauses, takes a breath, and experiences the wonder of its own existence. We are the rare, slow, precious part of reality that gets to say, I am. And as long as we respect the limit, as long as we understand the tempo, the music will keep playing. We don't need to conquer the galaxy to matter, we just need to listen to the song, because in the end, we are not the prisoner, we are the performance.